All right, I'm going to review what power is a little bit. So if you're doing a hypothesis test, power is the probability of finding a statistically significant result if the null is false. So if your null is really false, then you would hopefully support your research hypothesis. And so basically the power is finding support for your research hypothesis when you should. Okay? And the power for a confidence interval is the precision of the confidence interval. So how small it is. So you can determine power for either one. They're very related to each other. So again, power for a hypothesis test is finding a significant result. So it's a probability of finding a significant result when you should. And the more precise a confidence interval is, the more power you had. So having high power is a really good thing. If you have high power, that means you're really likely to find a significant result if your research hypothesis is really true and the null is really false. Technically, hypotheses are all about the null, and then you make this leap about the research hypothesis, but I'm going to talk about the research hypothesis as well to make it more understandable. Now, so I said that if you have more power, then you're more likely to reject your null if your null is really false, which means if there's really an effect, you're more likely to find a significant effect. And that's kind of what you're hoping for. Power is also useful when the null is really true. So you were wrong, but the null is really true. And that is because if you fail to reject the null, and the null is really, well, if you fail to reject the null, and you really don't know if the null is true or not, then having high power will help you. Because if you fail to reject the null, a couple of things could be happening. So maybe the null is really true and you're wrong. And so you shouldn't reject the null because it's true. Or you don't have enough power to detect this difference. And you have to get really lucky to find a significant difference. So if you have a lot of power and you fail to reject the null, then it's probably likely that the null is true. It's not 100% again, but it's more likely that the null is really true. But you need to have high power to kind of really determine that. If you have low power, then you don't know if it's because you have a lack of power or the null is really true. But anyways, so power is a good thing. How do you increase your power? Well, there's 4 things here, and you can kind of maybe cut them up into more things you can do. But I'm going to talk about 4 main things. So number 1, increase your sample size. This is probably the biggest thing you can do and the thing you probably think of first when increasing your power. So increasing your power makes you more sure of your results, right? If you have 100 people, then you're more sure of your sample mean than if you had 10 people. So the more sure you are, the more likely your p-value will be little, and the more power you have. Okay? So that's the basics of why sample size increases your power, but to get more technical, a higher sample size increases your degrees of freedom. Higher degrees of freedom increases your higher degrees of freedom increases the likelihood that your p-value will be smaller because the distribution will start to look more and more like a z. So a z-test is actually more powerful than a t-test also. So higher sample size means higher degrees of freedom, which means your p-value is more likely to be little and you're more likely to find a significant result. But also a higher sample size decreases your standard error, which increases your t-statistic, which in return lowers your p-value. So I'm probably a little confusing right now. If you want to know the details, you can start to write this down. And pause the video here. So if you have a higher sample size, that means the n is bigger. So if you put that in the standard error formula, right, for a one sample test, it is a standard deviation divided by the square root of n. If your n is bigger and you divide by a bigger number, then your standard error is going to be smaller. If your standard error is smaller, then when you calculate the t-statistic, the bottom of your t-statistic will be smaller. Thus, if you divide by a smaller number, you get a bigger number, and so your t-statistic is bigger. And the bigger your t is, the lower your p-value is, and the more power you have. Because if you have a low p-value, then you're going to reject the null. And increase your power. Alright, so we'll move on from there. Number 2, you can increase your alpha level. So remember, you compare your p-value to your alpha level. So if your p-value is less than your alpha level, then you have a significant result. So it's kind of the barrier of what you say is small, a small enough p-value. So if you make that barrier bigger by increasing your alpha, then you have more power because your p-value can be bigger and you still reject the null and find a significant result. Now, you don't want to do this really. You probably should stay with the 0.05 standard alpha level, but if type 1 errors aren't that much of a concern, maybe you can do an alpha level of 0.10 instead of 0.05. But don't make it like 0.20 just to have more power, because then you're going to have more type 1 errors. So it's a trade-off. So if you increase your alpha to have more power, you have more type 1 errors. And that means false positives. So false positives mean that you reject the null and support your research hypothesis when the null is actually true. Right? So it's a trade-off. So don't really do this. Don't arbitrarily increase the alpha just to have a significant p-value. But what you can do, which is more ethical, if you do this before you start your hypothesis test, not after. If you do it after, then it's not ethical. You're cheating. But if you decide to have a one-tailed test over a two-tailed test, then this will increase your power. Because when you have a two-tailed test, basically you're halving your alpha in half. Because you put half of it on one side and the other half on the other side. Or in other terms, you just double your p-value. And that's what Excel does. It'll double your p-value. And so if your p-value is higher in a two-tailed test, then you're less likely to reject the null because you have a higher p-value. So you have less power. Only do the one-tailed test if it makes sense. And the bad thing about having a one-tailed test, though, is if it's in the opposite direction, then you hypothesize. So say it's really less than, and you hypothesis a greater than research hypothesis, then you're kind of screwed because you said the other way, and you can't go back. But if you did a two-tailed, then you kind of have that catch of, okay, what if it's more than, or what if it's less than? But having a two-tailed test means you have less power. So it's a give and take there. Number 3, you can decrease your standard deviation. And to do that, you make a more reliable outcome measure. And so that just basically means you're more precise, you're getting rid of the noise in your outcome variable. So if you're comparing men and women on their height and you want to see if there's a difference in the averages, and you're measuring people but you're doing it sloppy, you measure one person and they're really 5'4", but you say they're 5'5", and then the next person who's 5'5", and you say they're 5'4", then this is imprecise and it's going to create some noise, some random error that is going to make your standard deviation inflate. And if you have a higher standard deviation, it means your standard error is also going to be higher. And a higher standard error means your t-value is going to be lower. And a lower t-value means your p-value is going to be higher. And if you have more higher p-values, then you have less power. So to decrease the standard deviation, you can be more careful and actually, measure people and then maybe double check and triple check to make sure you're not getting random error in your measurement that you can avoid. And if you do that, and this will decrease your standard deviation, which decreases your standard error, which increases your t-statistic, which in return lowers your p-value. I know it sounds a little bit complicated, but if you're not following all the way, just read the PDFs, even the PDFs from the one sample. One will help you, or just take my word for it that decreasing the standard deviation is helpful. Another way to decrease the standard deviation when you have a two-sample test is to have a dependent design over an independent design. And the reason that is because it removes individual differences. It removes the noise due to individual differences. So it removes that error due to individual differences. And so if you do that and you remove that, then the differences that you find, yes, some of it's going to be just random error, but none of it's really going to be due to individual differences. It's more likely it's going to be due to your intervention or whatever you're testing. So a dependent t-test reduces the standard deviation by removing individual differences. So generally, a dependent design is more powerful than an independent design. Number 4, study something that has a bigger difference from the null. And I'm talking about in the actual population, not with your sample means. So if you're trying to find this difference, it's easier to find a big difference than it is a little difference. Right? If you're looking at to see if people are different heights, you have two friends and you want to know if they are, which one's taller. I mean, probably one of them's taller. They're not going to be exactly the same height. That's probably rare. But if one's 7 foot and one's 4 foot, yeah, you can be like 100 feet away and tell that. But if, one's 5'4" and one's 5'4.5", so 5 foot and 4.5 inches, and the other one's 5'4", then you're going to have to be a little bit closer to determine that and look a little harder. So if you study something that has a bigger difference, then that test is going to be more powerful. It's going to be easier to find an effect because it's bigger. So for example, if you are studying gender differences, which I use gender a lot in this class, but you can compare other groups. But gender differences are just an easy example. But you could do like drug groups or something like that. So drug 1 and drug 2. But let's go back to the gender example. So if you're comparing men and women, it's easier to find differences in height than it is to find in mass scores. So the effect size for height is 2, And so that's 2 standard deviations, but in the averages, so men are on average are 2 standard deviations above women in height, but the effect size for math scores is just 0.16 standard deviations. And I calculate this from ACT scores, but that's a much lower effect size. These are Cohen's D's. That's a much lower effect size for math scores than it is for height. So if you just look around, you can kind of see that men are generally taller than women, and that's why you have this effect size that's so large. But if you look around and try to determine if people are better at math by just looking at their math tests, then it's a little harder. So number 4 is to study something that has a bigger effect size. So it's often helpful to know how to calculate the sample size that is required to achieve a certain amount of power. So if you're planning a study, you don't want to be underpowered, and you want to make sure that you have a high enough sample size. Because if you just have 20% power, that means only 25% of the time you'll find a significant result if there's really an effect. And so it's kind of pointless to do a study if there's only a 20% chance that you find this effect. So you don't want to be underpowered. So to do this, you need to know 3 things to calculate the needed sample size. The first one is the alpha level, and this is what percentage of the time you're willing to make a type 1 error, which is a false positive. So you say there's a significant result when the null is really true, and not the research hypothesis. So you're saying your research hypothesis is true and it's not, and that's a false positive. So this is going to happen. You don't know when it happens, but it's going to happen, and usually in psychology we put it at 5%. That's what we're willing to give up. That's the rate at which we say it's okay to have false positives. Okay, in other sciences, this might be different. I think in physics, it's a lot lower. Number 2 is to have your desired power, and that's usually 80% in psychology. So it means if there's a real effect different than your null, then 80% of the studies will be significant. So you'll be successful 80% of the time. There's really an effect. And power is 1 minus beta. And remember, beta is the probability of a type 2 error, which means you fail to reject the null when you should have rejected the null, meaning that there is an effect. So there is an effect, but you failed to reject the null. And you said it was non-significant. So you didn't find support for your research hypothesis when you should. So kind of the opposite of that is power. And that's why you do 1 minus beta, or 1 minus the type 2 error. If you don't remember what these errors are, you need to go back to the one sample mean phase. All right, then number 3 is the expected effect size, or the minimum effect size you want to detect. So the expected effect size means how big of a difference do you really expect to find. And so for these types of tests, you're going to do Cohen's D, which we talked about a little bit already. And to find the expected effect size, it's usually from previous literature. So you see what other studies found as their effect size, and you put that into your calculation for sample size. Now, the problem with this is that usually in journals, we typically only report significant results or results that have high effect sizes. And so we have this publication bias, and usually the effect sizes in journals, if you take the average of them, it's overstated. So having looking at previous literature effect sizes might be an overestimate of the actual effect size in the real world, because we tend to only publish results that look good, basically. And higher effect sizes look good, and higher effect sizes mean you're more likely to have a significant result. And that higher effect size, if you have a low sample size, might just be due to chance and not really because there's a true effect size that big in the population. So anyway, so effect size is correlated with your sample size. So generally, if you have a small sample size, we have to have a large effect, and sometimes that's just due to chance that we get it, and so we report it. And the studies with low sample size but small effects don't get reported because they're not significant, and so we have this bias. It's a big thing that you don't need to worry about right now. But anyways, usually the effect sizes in the literature are overestimates. That's all you need to know. So you might want to lower the effect size a little bit that you find in previous literature. Or alternative is you can pick the minimum effect size that is meaningful to you. So, if you only care about really big effect sizes, you can put it as 0.8. But if it's really meaningful to find an effect size that's small, like 0.2, then you can put it at 0.2. Or you can calculate power for different effect sizes too. Like you can say, okay, what if it's a small effect size of 0.2, if it's a medium of 0.5, or a big effect size of 0.8, what would my sample size is needed to be? And you can kind of see what resources you have and see what types of effect sizes you will be able to detect depending on your sample size and your resources. So, maybe you can only have a sample size of 100 and that's all you can do, but know that if you do a study with 100 people, you might only be able to detect, a small effect size depending on what you're studying. Or what your desired power is, etc. So 100 people might be enough for that, but anyway, if you can only have like 10 people, then no, you're only going to find a significant result if there's really a high effect size and you need more people. So just know, if you don't have a lot of people, you can only detect smaller effect sizes, and that's just going to be a limitation of your study. So you can pick the minimum effect size that's meaningful to you. So whatever that is, it probably just depends on what you're studying. Or you can take the average effect size in psychology, which is 0.4, if that's the last resort. If you don't know what to pick at all, you can pick 0.4. And again, this is probably a little estimated because of publication bias. So we only tend to publish a certain kind of results, and we don't really publish things that are non-significant. And we're trying to, in psychology and other fields, we're trying to correct this publication bias, but it's still very prevalent. So that's a talk for another class, but just keep that in mind if you're actually wanting to do research in psychology. Alright, I'm going to go over an example of how to use G-Power. You want to pick the test family. So for this example, I'm going to do a t-test. And I'm going to do a matched pairs dependent t-test. So I have two dependent means here. And then I'm going to stick with a priori. So you want to pick a priori if you want to compute the required sample size for your study. A priori means that you do it before you do your study. And this is generally the most helpful type of power analysis. The other ones that you do after you collect your data aren't as helpful depending on how you calculate it, but I won't get into those details. So this is the most helpful one. These are debatable, okay? And if you should use these or not. And then you want to pick how many tails you have. I'm going to pick a one-tailed. And then you want to pick your effect size that you think you'll have, or the minimum effect size that you care about and that you want to detect. So if a small effect size is something you don't care about, then don't put it here. If you're only worried about a big effect size, then put a big effect size here. And then you want to put your alpha level, which is generally 0.05, and your desired power, which is generally 0.80, and I kept it like that. Then press calculate. And easy as that, it tells you that you need at least 27 people to get a power of 80%. You can have more than that, but you at least need 27 people. So this only gave you the needed sample size for one effect size, but you can also do it for a range of effect sizes if you're not really sure what the effect size is. And that happens a lot. So you can press this XY plot for a range of values. I already kind of made one for you, but what I did was I kept this as total sample size here, because that's what I want to know about. And then as a function of effect size, you can also do it as a function of power if you're kind of are open to different powers. But more useful is the effect size function as a function of effect size. And so what I'm going to do is change that effect size, and then you can change these steps. So it starts at 0.1 and goes to 0.8. Steps at 0.1, that's fine. And then, you know, it already did this part for me, the power and the 0.05 from my other example, but you can change that as well. So in this graph, the power is constant and the alpha is constant. It's always 0.8 and for power, and it's always 0.05 for alpha. But what changes is the effect size and the needed sample size. So you can see if you only have a small effect size of 0.1, you need about 600 people. If you have effect size of 0.2, it drops all the way down to 150, and then it gets lower and lower the bigger the effect size. So if you have 0.8 effect size, then you don't need a lot of people. If you're doing a 2-sample independent test, then the only big difference here is the ratio of N1 to N2, or N2 to N1. And if you have equal sample sizes, then just put 1. If for some reason you can collect twice as many people in one of the groups in the first group, I don't know, maybe you're comparing college students to other people that aren't in college and you work at a college, then it's easier to get college students. So if you going to have twice as many people of college students, and you can put 2 here. And then the power, now I have the power of 0.95, which is pretty high. And so this gives you the sample sizes for each of the groups. Alright, so that's pretty much the same. You can also do this again, this plot. So again, I want to plot the total sample size that I need as a function of not power. You can do that, but I want to do it on the effect size because I'm not really sure what the effect size will be. So maybe you want to do 0.1 to 0.8. And you want 95% power, which is pretty high, and your alpha 0.5. Draw plot. And this is between 2 groups. And the ratio is 2. So you take the sample size it gives you, and then 2/3 of it is for the one sample, and 1/3 of it is for the other sample. So this is total sample size, not for each group. But again, you can see as the effect size increases, you don't need as many people. So this is kind of useful if you're thinking about a range of effect sizes that you're interested in. So say 0.1, you're not really interested in, and there's no way you can get 5,000 people. So when you're like, well, maybe I'm okay with finding only effect sizes that are above 0.3. So you can say your minimum is about 500 people for both studies with a 2-to-1 ratio. And so if you select that, you just need to know that you might miss out on finding effect sizes lower than 0.3 because you're underpowered. But if you only really care about effect sizes that are above 0.3, then 500 people would be good.